So let's tweak that situation a little bit here. Suppose that old MacDonald, our farmer here, has decided to make a fence against the barn. So he's got his pigs, like little Wilbur here, and he wants to make a pen now. Instead of just in the field, he's going to put it against his barn. Maybe something like this with the pigs can go in and out of the barn, but we're going to put a fence up against the barn. So he only needs to use 3 sides. Okay, what dimension should he use for the greatest area here? All right, so his pig pen is going to look like this. Here's the barn going on here, and here's the pen. Okay, well now the area is still length times width. That's still our primary equation because it's a rectangle. Again, we're assuming it's a rectangle, okay? And so the area here, the length, the perimeter is not 2L plus 2W, but now we only have one length because the barn is there. So we have L plus 2W. We don't need a second length. Okay, so we have 1L plus 2W. And we want that perimeter to be 200. So there's our primary equation and our secondary equation. So set this equal to 200, and we can solve for L. L equals 200 minus 2W. And now we can substitute that here, and we'll get an equation that we can optimize with calculus. So substituting there, we have area equals 200 minus 2W times W. And if we distribute that out, we have 200W minus 2W squared. Okay, now we need to optimize that. So let's make a derivative. That's going to be 200 minus 4W. And let's set that equal to 0. And so if we add 4W to both sides, 200 equals 4W. And so we get 50 equals W. Now, that sounds like the same answer. However, it's not, because when we plug that into here, the length is 100 minus 2W, which is 100 minus 2 times 50, which in this case, the length is going to be, I'm sorry, that's 200 there. So the length is going to be 100. So the best pen is 50 feet by 100 feet. Okay, now notice, by the way, we got a square on the last one. That's true. A square is going to give you the most area for a given perimeter. But here, in this case, where we only have 3 sides, this is actually, notice, a half of a square. It's half of 100 by 100 square. So that's useful to know. Our next question here, we've got a rectangle that is inscribed in a semicircle. And that means, inscribed means the vertices here are on the circle. They're glued to the circle. Well, a Desmos drawing can help out a lot here. So here's a Desmos example of it. So here we have the rectangle, and we've got lots of different options here. All right, and so what's the area going to be? Where is the area going to be a maximum here? Okay. Well, and by the way, you can go type this in to your web browser. You can check that out. Just copy that number down there. All right, or you can build it for yourself. So, where is that area maximum? All right. Well, to find this out, we want to kind of generalize this here. So what we say is we've got a point. We're going to pick a point here. We don't know where it is, but let's say it's x comma y. So that is the height here is y, and this distance from the origin is x, right? Well, this is in a circle, so this is also going to be x to the left. It's going to be symmetrical because the circle is centered on the origin here. And so, and a height of y. So let's make our equations now, all right? So our primary equation The thing we want to maximize is the area. So we ask ourselves, what do you want to be the largest? Well, here we want the area to be the largest. Area is length times width. Okay. Or in this case, area is 2x, because that's how long it is. Not just x, it's 2x times the width, or y. Or base times height, if you want to think of it that way. Now the secondary that we know is this equation, y equals the circle. Y has to be equal to the square root of 4 minus x squared. That is a semicircle, which is the top half. And so we want to use that secondary equation to solve here. So we're going to plug that in. We're going to substitute. And so we get area equals 2x times the square root of 4 minus x squared. Now we need to find the derivative of this, right? We want to maximize the area. So a prime is going to be, well, we need to use a quotient rule here. So derivative of the first is 2 times the second, square root of 4 minus x squared, plus the first times the derivative of the second, which will need a chain rule. So we need the derivative of the inside, which is 2x, times the derivative of the outside, which is going to be 1 over 2 times the square root that's given to us there. Let's squeeze that in here. So we're going to have 1 over the square root, 2 times the square root of 4 minus x squared. All right, I think we got all the parts there. Let's clean this up. So we're going to need to solve this. We're going to need to set it equal to 0, but we got to clean it up first here. All right, so we have, well, this 2 is going to cancel with that 2. And then we have a 2x here, right? So we've got actually an x times a 2. So that's a 2x squared all over the square root of 4 minus x squared. And over here, we have, let's actually write this a little different way. Let's write this as a negative 1/2 power. You'll see why in a second. So by writing that as a negative 1/2 power, we're going to be able to factor this. And so we have 2 times the square root of 4. Well, let's write this as a fraction also. 4 minus x squared to the 1/2. Now we're going to need to set this equal to 0, right? So let's go ahead and do that. And how do we solve an equation like this? Well, we need it to be factored. So the reason why we wrote this up like this is now we can see we have 2 factors that are the same. When you factor, you're going to pull out the smallest exponent. So we have 4 minus x squared to the 1/2 and 4 minus x squared to the negative 1/2. So let's pull out the negative 1/2 here. 4 minus x squared, and let's go ahead and pull out a 2. So we pulled out a 2, and 4 minus x squared, well, we're going to subtract it. We're dividing this by this, so we're going to subtract 1/2 minus negative 1/2 is a positive 1. So this is going to be 4 minus x squared to the first. And we pulled out this, so all that's left is the 2x squared, so actually just the x squared, right? Because we pulled out the 2, we pulled out the 4 minus x squared to the 1/2, or negative 1/2. And we got that here. The x squared become negative 2x squared. And so we have 2 times 4 minus x squared to the negative 1/2 times 4 minus 2x squared. Okay. We want to find our critical point, set this equal to 0. And this is 0 when 4 minus x squared equals 0, or 4 minus 2x squared equals 0. One of those has to be 0. So 4 minus x squared equals 0. Add x squared to both sides. Square root x equals plus or minus 2. Our second equation, 4 minus 2x squared, let's set that equal to 0. Subtract 4 and divide by 2, and we get x squared equals 2. Now square root, we get 4, or x equals plus or minus the square root of 2. Now, what's going on here? Well, if x is 2 or negative 2, then that point is coming all the way down here. And that's going to be a really flat rectangle there. Okay? So that's going to, if x is 2, the area is going to be 0, right? Because that's a 2 by 0 rectangle. So that's actually going to be a minimum. Remember, we just found the critical values. So critical values find minimums and maximums. So this is going to give us a minimum. But if we try the square root of 2, and you plug the square root of 2 in there, that's going to end up giving us a maximum, all right? So we want this point to be the square root of 2, and we got to find the y value, all right? So we're going to use this equation here, and when you plug in the square root of 2, we get the square root of 2. So x equals the square root of 2, and y equals the square root of 4 minus the square root of 2 squared. That comes from here, the circle. And so that's the square root of 4 minus 2, which is 2. Okay, so y equals that, and x equals that. Okay, so the largest possible area will be at the square root of 2, square root of 2. Okay, and you can kind of look at it there. Square root of 2 is 1.414. And so if we take this to about 1.414, getting close to that there, all right, and that looks like our, well, it is, it's a half of a larger square, or 2 small squares, you can think of it there. So that's the idea, okay? All right, a couple more here. Here's some classic questions here, optimization, okay? Find two positive numbers that have a sum of 10 but have their largest product, all right? And you can go through and guess and check this pretty quick, but let's try this out. We want it to be the largest product, so maybe P for product equals x times y, the two numbers multiplied. But then we know x plus y has to be 10. And if you solve this, y equals 10 minus x. Let's substitute. The product is y. Nope. We're going to substitute for y. So we're going to put this into there. And so we'll have x times 10 minus x. And if we distribute, we want to maximize this. So p is 10x minus x squared. We want to maximize this, so we want to set the derivative, p prime equal to 0. So derivative is 10 minus 2x, that equal to 0, and we see x is 5. And since y is 10 minus 5, then y is 5. Okay, and so the product, I'm going to find the largest product. The product is 25, 5 times 5. That's the largest you can get. Okay. All right. One more type of problem here is when we have a curve and we want to find the distance between a point and a curve. This can be pretty useful. So if we have a curve, y equals x squared. Looks like that, y equals x squared. And we got a point, 1, 2, 1. Okay. And so the point up here would be 2, 4. But we want to find the distance here. So what's going on is we want to find the distance between 2, 1 and the graph there. Okay, what is the shortest distance there? If we go over here to this point, that point's a little longer. If we come over here, that's a little longer. The shortest distance is going to be actually perpendicular to a tangent line there. Okay, but this is the point we'll call x comma y. So we want the distance between these 2 points, x comma y and 2, 1. We want that to be minimal. Well, how do we find the distance between 2 points? That's the distance formula. So our distance formula for coordinate distance is x2 minus x1 squared plus y2 minus y1 squared. All right, and so we want that. We're going to plug in. Our 2 points we're going to call xy and 2, 1. Okay, so our distance is the square root of x minus 2 squared plus y minus 1 squared. We want to make that a minimum, so we've got to find the critical values. So we've got to find the derivative of this. So this is going to be, well, first notice this. We can't find the derivative actually yet because we've got 2 variables, right? Yeah, you might be thinking implicit. We could maybe think of it implicit, but we have another equation we forgot to mention. That's y equals x squared. Since y is equals x squared, we can put that in there, all right? And so the derivative equals the square root of x minus 2 squared plus x squared minus 1 squared. All right? And so we'll take the derivative here. If you want, let's go ahead and maybe simplify this out here. Might be able to clean that up. Might make the derivative a little easier. So we've got the derivative equals the square root. Squaring the binomial, we get x squared minus 4x plus 4. Square this binomial, square the first, we get x to the 4th. Square the last, we get 1. Multiply and double minus 2x squared. And if we clean that up, we get x to the 4th. And we get minus 1x squared. Put the x squareds together there. And then we get minus 4x and plus 5. We've got it all there. So now we can find the derivative of that distance. So d prime, we're going to want to set that equal to 0. So this is going to be, derivative, the inside is going to be 4x cubed. Minus 2x minus 4. All right, yeah, that looks pretty good. And then all over, so the derivative of the square root is 1 over 2 times the square root itself. Okay, x to the 4th minus x squared minus 4x plus 5. Now, this is going to be one, we want to set this equal to 0, right? Or we want to find out when it's undefined. Okay, it's undefined when this is 0 down here, and it's 0 when the top is 0. So to solve this, we're going to use our CAS calculator, our TI Inspire CAS. So to use our CAS calculator here, we're going to, on the handheld, go to Menu, then we're going to go to Algebra, whoops. Find our algebra, solve, and we'll type our equation in there, 4x cubed. This is for the top of the equation here, whoops. 4x cubed minus 2x minus 4 there, all right, 4x cubed minus 2x minus 4, and we want to set that equal to 0. So equals 0, and we want to put comma x. We're telling it what we can solve for there, okay? And comma x, there it is, okay. And there's our answer, 1.1653, okay? So x is approximately 1 point, let's get that again, 16537. And then we want to look at the bottom, okay? What makes this, well, this can be 0, the square root of 0, I'm sorry, it can't actually, because the square root of 0 is 0, and that would wipe it out. So let's try x squared minus, I'm sorry, x to the 4th minus x squared minus 4x plus 5. So we're going to solve again. We go to algebra, solve, x to the 4th we had, and then minus x squared, better check, minus 4x plus 5. Minus 4x plus 5, set it equal to 0. Okay. And comma x. Actually, we want, we can't be less than 0. And actually this says, yeah, false means that there is no solution. That's what false means, okay? And so we should be fine here. Let's double check x to the 4th minus x squared. Make sure I typed it in right. Minus 4x plus 5. Never is equal to 0. It's always going to be positive there. All right? So that's great. Okay? So we don't have any others except for this one. So we've got the x value there. Now we need to just square that. And when we square this, because y equals x squared, so we get 1.358. Y equals 1.358 for our y value. And we can approximate this, round this up to 2 decimal places is good. Okay, and so there's our answer. There's our xy points. That is the closest to 2, 1. All right, so now we found it. We found the point that was closest, that lives on the curve. This point lives on this curve because y equals x squared. And it is the shortest distance from there to 2, 1. Okay. All right, hope that helps. That's how we find our optimization or solve our optimization problems. We set our primary equation. We want to substitute to get just one variable. Then we're going to take our derivative and set the derivative equal to 0. That'll give you the critical values that you can test out. That should be your min or your max. Thanks for going through that with me. A lot going on there. Hope that helps. We'll see you next time.